So, apologize for a meeting like this. Not my preference to do it over Zoom. Actually, I do rather enjoy it, but not my preference to change up the mode of lecture without giving people plenty of warning. But I wasn't really feeling that great last night. I got whatever my kid was sick with last week. I'm assuming it's the same thing. Um, just not, it's not terrible, but it's not fun. And I just want to pass it on. So, so. So I'd rather, do my presentation like this. We are going to be working on one of the course projects over Zoom today. Um, and I'll be recording this just to make sure that everybody gets the chance to do this. As always, we're going to deal with administrative stuff first. So I'm going to briefly share my screen. We are going to go to the course modules. This is week 4. Turtles, sequences, and for loops. So, again, here's more material for you to check out on those on the for loops and turtles and how to use them. Again, either read the textbook or watch these videos or both. Um, this is what is assigned to you, and the lab you'll be issued. The main reason I'm coming here is that the lab you'll be issued this week. The loops 1.pdf is this. It is there's a bunch of things that you should know. The first is that we will be writing these problems as functions. And if you don't know what that means yet, that's fine. But we will but I go over that in the text as well as a link to the appropriate runestone assignment. Although that one is apparently rather old. But the appropriate runestone assignment over there, as well as hints as to how to print things in a more special manner. But this is a larger assignment. Note that it is lab 4 and 5. So this is what we expect you to be working on in lab this week and next week. If you're able to get it done earlier, great. If not, well, there's a lot of things to learn in here. So first off, printing, there are 3 standard kind of what we call loop problems that we give to freshmen. These problems are pretty much no different than you'd be able to see anywhere else. So this one is classic 99 bottles of beer. You can, of course, replace that without any beverage you want, but it is 99 bottles of beer on the wall, which is a drinking song in the US. I although I've never actually heard anybody sing it in that context. I've actually only, the most I've ever seen it in the context in any context is a programming exercise, oddly enough. So the idea here, though, is you take input from the user, and it will print out the lyrics of the song descending. So if the user inputs 10, they'll print out 10 bottles of beer on the wall, 10 bottles of beer, take one down, pass it around, 9 bottles of beer on the wall. And then we'll continue on to 9 bottles of beer on the wall, 9 bottles of beer. And then it will go to 8, and then 7, and then so on and so forth. And note that I don't really care about the pluralization, right? We're not at that level yet to say one bottle as opposed to one bottles. That's okay. But this is a classic kind of loop problem where we will print something again and again, and something is going to vary each time we print it out. A variable. Multiplication table is one of those that require you to use nested loops, a loop within a loop. And it's not as hard as it seems, but it is tricky to get it your very first time. Once you get it, it's often a matter of case of how did I not see how to do it before? But it prints out a multiplication table. This one, last one, the summation of squares, right? A function that gives an integer n uses a for loop to print out the sum of all numbers squared run to n. So in this case, I say if you enter in 5, you should get 55 because 1 squared plus 2 squared plus 3 squared. And a lot of students accidentally interpret this to mean that I want you to print out 1 squared plus 2 squared and give me a lot of students interpret that as I want you to print out this. For that problem, I don't want that. All I want for this problem is that if you give me 5 as your input, I want 55 as your output. These problems may look very difficult right now, and that's okay. We still got 2 lectures to go through, plus your lab sessions. Um, so the other one is these turtle functions. And what they are is that this is to teach you the importance of functions to make things much more easy for you. Because without functions, you'll be having loops within loops within loops within loops, or something to that effect, and it will be rather aggravating. Making functions allows you to abstract things out. And if you haven't gotten to the point where you're reading functions yet, or understand what a function is, the idea behind a function is that we're dealing with a programming language, right? So languages can be modified. English is modified all the time. New words are added. Uh, Different words get a different meaning. Um, so Python is similar. What def means over here is that's short for define function. And what that does is that it creates a new verb in the Python programming language, a new action that can be performed. I like to think of these as verbs in this case because they are actions that your computer will do. So here you would be creating a action that has a turtle draw a square, then draw a row of squares, then draw a grid. And the idea here, well, this over here where we are drawing a row of squares is drawing a row of squares. So we are doing this verb multiple times. And the same goes for drawing a grid. This is not just a grid of squares, it is multiple rows of the same size. So I could draw multiple rows. So draw grid, we'll be able to call draw row, which in turn will call draw square. And then finally, drawing a square stairs. The exam won't have anything nearly as difficult, so if you're able to do these and understand how these work, you're going to have a fairly easy time on the exam. And then finally, this should look fairly familiar to what you've done or what you're doing or have done in Lab 3, creating an n-sided polygon. And then we use that to build this, which looks rather difficult, but it is not too bad, actually. Because what this is in this case, I used this function to draw a hexagon. This over here, it may be hard to see, but it's actually made up of multiple hexagons. Let's see if I can't. Yeah, I'm not great at tracing. But you get the idea. This is made up of multiple overlapping hexagons. So this is just giving you a preview of what we're working up to, and also giving a chance for any stragglers to join late. We've got about 2/3 of the class here, so that's not too bad. So here's what we're going to do. First, I'm going to discard the pen tool. Clear. Today's exercise, we go to our modules. We're over here. You'll see that over here, we have Tuesday, we will be looking at creating random passwords. And normally I'd tell you to go ahead and click on and navigate to this and click on it. But we're online today. I can just drop it to you. I'm going to drop it in chat. So you'll be able to get that no problem. So here it comes. Everyone meeting. And there is the link to today's exercise. Make sense? So we can go ahead and get started on this exercise. All right. So I'll give everybody a chance to click on it / log in if they need to, and then I'll start going over it. Okay. That's just the function to annotate. All right. So one of the things that Temple does really well security-wise is their campus security policy for passwords. You may have noticed that the longer your password is in um, for Temple, the less kind of characters you need to add. So if you're doing only 8 characters, you have to put in that normal gibberish of weird symbols. But if you put in something, say 16 characters long, you're allowed to use just undercase characters if you want to. And and this is a wonderful comic, XKCD. We've seen references it to multiple times in this textbook. And over here, this one goes over basically the nonsense that typical password rules are. Typically, when you make a password, you've got some uncommon. All right, let me grab my annotator. We annotate. Where is that? No. Annotate. There we go. Typically, when we create a password, we have to go through a lot of gibberish. Namely, we grab a word over here like troubadour. Okay. And that's typically used as a word. Typically, it uses some kind of, yeah, and it's typically not gibberish. Then you have random capitalization. You might put that, typically, you put that at the beginning because that's easy to remember and you only have to shift once there. And a common thing to do is replace various letters. In this case, O with 0, A with 4. Another common substitution is E's with 3s, or an L with a 1. Something that's rather easy for a human to remember. Those kinds of substitution. And then you might create a password like super hat. And let's make it 8 characters long. Super hats. Right? And then it might ask you, oh, you didn't put in a number or a letter. And if you're lazy like me, you might do something like an exclamation point and then a number, right? It doesn't matter. The point being is that this is not actually that great. We have this over here. So we're working with this password as an example. This is approximately what we say is in the information security 28 bits of entropy. And there's a website called Explain XKCD, and you can look this comic up. It's 936 that goes through the calculations as to how you get to that entropy. So, but the point being is that you have basically this is basically the number of bits of uncertainty, the different permutations of bits that can be used to represent a password of that same length. And it says with 28 bits of entropy, you've got 2 to the 28. How we calculate that, you don't need to know. Point being is that this number is how strong the password is. And this was written like 10, 20 years ago. So it's probably even worse now. But the idea here is that it would take 3 days at 1,000 guesses a second, which is not a terrible assumption for a computer for a computer. Difficult to guess, easy. And then trying to remember it though, it's hard. The idea here is that password is hard to remember. Was it troubadour, trombone? Was it what got substituted? Was it the first one or the second one? What in the world did I put as that symbol? It's hard to remember. A much better and stronger password to use is to take four random words like this and use that as your password. Correct horse battery stable. This is much more what's, again, entropy for the computer. And we're going to see that in action later at the very end of the lecture. But the idea here is that it takes this, the difference between 2 to the 28th and 2 to the 44th is massive. 550 years for a computer to guess that at 1,000 guesses a second as opposed to 3 days. Hard for a computer. How hard is it to memorize for a human? Easy. Correct horse battery staple. Forward. So this is the idea here. So what we're going to do is we're going to learn how to build these passwords. We're going to make a password generator today. The idea here is that we are going to first start by creating this random traditional password like this one. Only we're going to do it much better, and rather than using a base word, we're just going to use random gibberish. The idea here is make an 8-letter password by combining characters from 3 strings. So rather than, and they were very kind here. You can see over here that they gave us letters, capitalization, capitalized letters, and numbers. Okay, so those are already in play for us. We don't have to go through our keyboard and type out A, B, C, D, E, F, G. We don't have to go through and do that. That's very nice. We need one more tool to make this work. We need one more tool to make this work, which is we need to import random. Now, now we've used the turtle library to do things. We've used turtle to go ahead and draw graphics, draw lines, make shapes. Random is for dealing with pseudo-random numbers. The idea here is that we kind of skirt the entire philosophical argument of is anything truly random if you can like calculate if you know all of the all the positions of everything beforehand and the physics of everything. We skirt we don't deal with that nonsense. That's for philosophy class. Instead, we just claim that everything is pseudo-random. The idea here is that it is statistically random or close enough for us to use for our purposes. What this means is that we can treat it as being able to do random stuff. Typically, we use this for like random. Let's see, random dot next. Is it next int? I always forget this for. I always forget this for this. That might be the Java syntax. That is the Java syntax. Random dot float. Randomized. What is this? Sorry, it's been a while since I had to use random. So let's go ahead and do, because I only really use Python. With Python, the way it works, I only really ever use one function for it. That's pretty good. So, but if you can't ever, but if you're in a situation like me and you can't remember, what do? Random, and then doc, and then Python. Generate pseudo-random numbers. And you can find, for any library built into Python, you can look it up. And if you're very interested in the base mechanics of this and want to go way too much into depth, you can look up the paper on how random numbers are generated. Rand range. That was it. Rand range. So you can do things like rand range, which goes, let's say 0 to 5. That will go and give me, oh, right. It's going to give me nothing because I didn't print anything out. And still not going to print anything out if I can't spell. It's going to give me a number from 0 up to, but not including 4, just like the range function. Basically, it picks a random number from the range, just like the range generator does. What about other ones? Randint, that's more traditional. Typically, this is what's used. Randint basically says this would be the same as rolling a 6-sided dice, where basically we have one where we can get any number from 1 to 6. Right? And yeah, you might get something like, oh, 2 6s in a row. That doesn't feel random. 1 6, another 6, another 6, another 6. No, that's random. That's if we do enough of dice throws, that's going to even out. Okay. So random's pretty awesome. Now, one of the things I really like, but for Python, what I really like is this. Random.choice allows you to do allows you to say, given a collection, or sorry, a sequence is the term in Python. A sequence a sequence that's a string or a list. So given a sequence of things, something that contains multiple other things, pluck one out. Not remove it, but like just point to it and choose it at random. Like so. And this chooses a random letter. Now, if I didn't have letters to find, of course, this would crash and burn, right? It's only giving me a letter because I have letters equal to the letters A through Z. If I didn't have it named something sensible like that, I would have to, you know, I'd be having to call the other variable name. And then I can do the same for caps. And that will select a random capital letter. So our goal is to make a 8-letter password by combining characters from 3 strings. So how do we go about doing this? Now, we touched on this back on Thursday with the calculation for pi, but it's the same principle. We're going to use the accumulator pattern. This time, we're going to use a string to do accumulation. What do I mean by that? Typically, when I'm building something, I might give it a variable name like output or answer or something like that. I could also call it password if I wanted to. Why not? Password is equal to quote, quote. That's the empty string, right? If I print that out, it's not going to, let's see, gives me a warning that it's not random's never used at the moment. That's fine. But there's nothing there for me to select. Whereas if and so that's an empty string. Whereas if I had a space, I'd have a space there to highlight. Empty string is effectively the string version of 0 for integers. So what does this mean? This means we can use an accumulator pattern on it to add to it. For instance, for blank in range, because I don't care about having a variable, there's nothing that's going to change over time. For blank in range, and let's say I'm going to do this 5 times. Password is equal to password plus A. Now remember, when we do concatenation, when we do addition with a string, it's called concatenation. So what we do is we continually glue A to the end of password. So if we print out password, what happens? We go through, we get, again, showing code lengths right over here. For IAM range 5 password. So we have our range, password adds A to it, then it adds another A to it, then it adds another A to it, until it goes through this loop 5 times and prints out our password, which is not particularly good password. So so over here use an accumulator to build the string. And then over here, what we're going to want to do is get a random character. And then we're going to want to add that, rather than adding A, we want to add that random character. Okay. Use accumulator to build a password, get a random character, and add that random character. We saw how to do that. We would use something like random.choice from whatever the sequence was. Now, the only issue is that we have three separate sequences here. And random.choice only takes one sequence. So what do we have to do here? We can use Python to, before we get into this loop, we can use Python to combine letters, caps, and num into a single sequence. So I'll give you about 5 minutes, 3 to 5 minutes to work on this, and then I'll come and show you the answer. So I will go ahead and close this and all right. Make sure you import random if you didn't, but let's go ahead and take a look at how this one works. So over here, and it's okay if you didn't get anywhere close to being done with this one. If we had more time in class, I'd give you more time on this one, but I want to make sure that we have the chance to get to everything we need to get to. And so what's important is, did you at least start thinking about this problem and get there and start getting the beginnings of a solution? Okay. So what we have here is we have this password and we want to build it. We want to build it out of these elements. Now we can build the hardest part of this, I think, is actually the easiest part once you see it, but coming up with it is the hardest part, I think, which is combining letters and capitalizations and numbers together into a single combined sequence, like so. So cars is equal to letters and capitals and numbers. So password. So we are over here with password. Yes, I'll be putting this on YouTube. Don't worry. So password for blank in range 5. We want to do this for 8 characters. And so you may have gotten here at some point, which was, hey, we want to get a random character. Let's go with C for character C is equal to random dot choice. And then letters. You might have gotten there and you would have realized, okay, if I do this and then add C to it and then print out the password, you'll only get a password made up of lowercase characters, a random one made up of lowercase characters. Same if you did caps, right? But we want a password that's 8 characters long and is made up of randoms of all of these. So that's important. That's why we do this step right over here. Cars is equal to this. Oops. Cars. And now if we run it, we get really interesting gobbledygook, right? So over here is the next step to that. And it is almost exactly the same. It is almost exactly the same, but our lists are different. Okay, we have different pieces. Instead of having letters and numbers and capital letters, we have nouns, verbs, and adjectives. So we're going to do the XKCD way this time, where we have nouns, verbs, and adjectives. We have tissue, processor, headquarters, favorite cure, ideology. So ideology? Yeah, ideology, funeral, engine, isolation, perception, hat, non-secession, cake, legislature, consent, spread. So we've got all these words over here from, okay? And the idea here is we want to make a 4-word password. And once again, this works just as well on any sequence as any other sequence. So random.choice nouns. Oh, I got to remember to import random. I forget to do that too. The key is to be able to know to know why you're having that issue. So here, and that's just going to choose a word from this list at random. Not a random character, because a string is a sequence of characters. Here, this list is a sequence of strings, so we're grabbing the entire string from it. Okay, so make a random. So here, what we want to do is that's pretty much the exact same as this part. In fact, I'm going to leave this part up. I'm going to share the code, and I'm going to leave it up right here for this next part, which is you want to now build the password from 4 random words. All right. So let's go ahead and give you another, let's say 3 to 5 minutes on this. I'll give it to 240. So go ahead and work on that until 2:40, and then I'll probably be taking over for the majority of the rest of the lecture. Okay, so let's go ahead and see how to do this. This one I find very interesting in a lot of different ways to do. It presents a lot of different interesting kind of challenges, believe it or not. Specifically something called the fence posting problem. But we will burn that bridge when we get to it. So once again, this let's go ahead and combine these all into one thing rather than combining it into a variable called cars, right? We're going to use meaningful variables. This was cars because there's our individual character glyphs. Whereas over here, I'm going to combine these and I'm going to combine them into a single list called words because that's what they are, words. So we're going to do nouns plus verbs plus adjectives and print words. And it's going to give me a warning that random has not been used yet. That's fine. But now we have one mega list, right? See, here's an adjective, the last adjective of this, American. And the first is tissue, which is this. So that makes sense. All right, so now they're together. We are going to make our password just like we had done previously. Same deal. We're going to make a empty string. We're going to print that empty string when we're done with it. So, well, hopefully it's not going to be empty after we're done. For in range, because we want to take 4 random words. We're going to do this random operation 4 times. So now we're going to go say word is equal to, and this might bother you. This makes a lot of sense to me. If this bothers you, don't do it. But I like to use plural and singular, right? When I'm grabbing something out of a collection, like to use the word uh the a plural variable name for my collection. Random.choice words, and I use a singular. And that can be very tricky if word and words to look too similar to you. If that's the case, maybe just use W instead. Right? But select the random word from the words, and then we're going to go ahead and add that to our password. Password is equal to password plus word. And so we've got kitchen impose operate shorts, or finish advise fragment repeat. So a couple things here. First off, doing password is equal to password plus. That gets tiring. We've done it a million times. Fortunately, there's a shortcut. This is exactly what this and this are exactly the same. It's exactly the same thing, just shorter. Plus equals. Password plus equals word. So we add a word, and you can see there. It's printing twice because I've clicked on it so fast that it did something weird, I guess. So now it's a bit hard to tell what these words are, though, right? And besides, when I'm making a password of random words, I like to put spaces in between them. You can put spaces in password. Why not? Why can't you put spaces in your password? It's rather silly that to think you can't, because that's how I would remember it. So let's go ahead and add a space. Now, everything over here on the left side, everything over here on the right side of an equal sign will be get done before we do an assignment statement, even if we have this plus equals here. So when we run this, we get intense, encouraging fragment handle. A lot easier to read, a lot easier for us to remember. I can just type that rabbit space persist space inspire space informal. So I'll go ahead and copy this into my password manager, and then I will go ahead and when I'm asked to make a new account, I'll put this in as my password, and that's going to be no issues. And then I'll go to log in and I'll type in my password, and it's going to give me an error. But I type it in rabbit space persist space inspire space informal, and it will keep telling me that my password is wrong. Why? Because hidden characters stink. Remember, what we're doing over here with this one is that let's go ahead and just transition this back out. And that is why and that is why we're at home today. Oof. Password is equal to password plus word plus space. So we're going to take whenever we add a word, we're going to take whatever the word is, add it to the end of the password, and add a space onto the end of that. So we add rabbit space, persist space, inspire space, informal space. And if I didn't catch that fact that I have a space after informal, then I'm going to be in trouble. This is what we call a fence posting problem in computer science, where basically whenever you build a fence, okay, whenever you're building a fence, you've got your fence posts. Okay, we've got our little posts laid down. We've got 4 fence posts. But to connect the posts, we need 3 pieces of fencing, right? 1 piece of fencing, 2 pieces of fencing, 3 pieces of fencing. So we need 3 pieces of fencing, but we have 4 posts. Now, how you get around this differs from one from problem to problem. It depends on the specifics of this problem. Heck, depending on how you do it, you may not even need to deal with it. For instance, if you know how to do in Python, eventually, not yet, but eventually you'll learn how to do slices correctly. It'll like second nature to you, and I can go, I know how to do this. -1, boom. Bracket colon -1, and that will just simply chop off the last character. And now I can do that. That's no problem. But what if you don't know slices? How can we use what you already know to get around this? Well, in this case, what we'll do is this is not elegant, I wouldn't say, but it works. Do it 3 times. So you get your fence, you get your post, your fence, your post, and your last piece of fencing. And then you still got to put in that last piece of post. And so we'll do so right here outside of the for loop individually. Password is equal to password plus word. No space this time. And that will give us profession invest bottle bottle. I've never seen that happen before where I get the same word twice, but it's random. Remember? Random doesn't really care if it looks random or not. Right? Something now it's happening each time for you where you're getting the same thing over and over again, then it's probably something's gone wrong. What you got to make so are you does your how much does your code look like mine? Or are you getting the same outcome each time? Let's see. Oh. Hmm. Oh yes, I see what's going on. Ah, okay. Yes, that makes sense. And that's pretty simple as to why. Because I have word declared here, and we create a word. And then outside here it says, oh, what's word? Well, it's the same thing we added over here. Right? We didn't choose another random word over there. See, even I make mistakes. And now that should fix that. Hmm. We weren't changing the word. Or if we want to, we can just simply say, if we want to still use word, we can do that over here by saying word. There. Share code. Okay. Typically, I'd be spending more time going around the class and going through these with you or answering individual questions. Um, this part not particularly interesting because I feel I don't like this part of the exercise, to be honest. This one, because it says basically, hey, that work you just did to not use symbols, let's undo that and replace random letters with symbols. What's important though is to go ahead and save and run this part. And we will actually take a look at the thing they're trying to show us, which is actually very useful, which is replacing one word, which is some good string functions. First, you can replace one string with another. For instance, it shows us, hey, if we've got a word called pool and we say to replace the O's with E's, then it'll do so. Right over here, we've replaced pool, the O's in pool with E's to get peel. Now, one of the things to keep in mind is that I think I should be able to do this with any string. So here I replaced the O, I said replace any O with 3 exclamation points. So the first O was replaced with 3 exclamation points. The second O was replaced with 3 exclamation points. Right? The least surprising thing there. The other thing we could do is we could say, hey, replace the double O. Oh, let's see if that works. Replace the double two. If I see 2 O's together, replace it with an E. That can be very useful. And finally, if I wanted to replace, if I wanted to replace P with blank, that'll work too, I think. And that'll give me ool. So word, and so the other one that I find useful is word dot capitalize. There's a couple of different ones in, there's a couple different functions in Python which are super useful for strings. One is capitalize, which applies capitalization rules. Word plus, so over here, if I do pool, um, pool's rule, okay, and I do that, I'll get Peel's rule. Whoops, that was just that. Pool's rule, and then it will capitalize the beginning of the string. Right, so it's not just capitalizing word by word, it's capitalizing just the string, like it's a sentence. So now let's go ahead and look. What if you wanted everything capitalized? You would use upper, and that makes everything shouty, right? Word dot replace. Good question. It's the latter case. It's we use word dot replace because word is the variable here. It's the object that we are and that object has a function in it, to use the technical terms. But basically, because it is a thing that has a action built into it, we use dot replace to call that action. Basically, there's two types of function. Broadly speaking, there's two types of functions. Um, the one that you basically see as action and then thing, and then the other way of writing it, which is action, sorry, which is thing dot action. We call this first type a function, and I've called it a verb. In this case, this is often called a method, and we're getting way ahead of ourselves here. And this is essentially a noun performing a verb. And for right now, basically, you'll be using it's a matter of kind of remembering which one to do. But for the most part, if it's not a built-in function to Python, like len to tell how big something is, or int to convert something into an integer, or 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 float to convert it to a float, or input to get an input, then you're going to be using the way it uses a dot. The way you can kind of, and I can't just tell you to memorize it because that's not very interesting. So what's the rule? If it's a function you can use on anything, then you just do it like this, right? Because that's got to work on everything. Same with int. You got to be able to do it on any kind of input. Same with input. On the other hand, if you're only trying to affect a specific thing, it's going to look like this. So there is going to be a bit of a memorization there, but it's not so bad. So the last part of this is what I find to be very interesting, because we're going to be importing a few different things here. We're going to be doing the opposite of password guessing. Okay. Sorry, opposite of password making, which is password breaking. So the idea here is that we're going to look at this program and we're going to add to it to make ourselves a password cracker. Not a very good one, by the way. Really silly one. So let's see what we're given. Import random, import sys. Sys is useful for system things, like in this case, sys.sec execution to 60,000. This is in milliseconds, so 60,000 gives us 60 seconds. Remember how I said your program will automatically crash after 30 seconds in your textbook? This just changes that so that it will um, crash after 60 seconds instead. And this is again to prevent the web page from hanging and grabbing everything. So let's look at this. My password is ABCD. So that's the password we're going to try to guess. I know we already know what it is, but we're going to be trying to guess it. And what we're going to do is we're going to see how many guesses it takes for us to figure out what that password is. Done is equal to false. So we haven't really seen Booleans yet. Booleans, right? We've seen integers, right? 1, 2, 3, 4, integers like that. We've seen floats, which are like this, except they have decimal points. We've seen strings. Booleans are the last one, and they fortunately only have two values, right? A Boolean only has two values, right? It's either true or false, one or the other. It's used for basically true, false statements, and they're useful for things that are conditional, where we have to make decisions. So over here, we're saying done is equal to false, and I very much like doing it like this because it allows us to figure out what the next part is. While not done, and then we have a colon which says, hey, this is an indented statement, so you're going to be doing everything in here. This is what we call a while loop. Programming languages typically have two types of loops. We call them definite and indefinite, although the line can sometimes get blurry because you can often use one you can often rewrite one in the other. So over here we say while not done. So this is going to run so long as done is false, because what this is, as long as this whole statement is true, it's going to keep running. Done is false. So this wouldn't do anything if it was while done. I'd just run it and it would stop. While not done takes that false and flips it to a true. But if you read it, it kind of makes sense. It says, hey, while this is not done, keep doing this. And what we'll do is that we will say, hey, when we're finished, we're going to set done is equal to true, so the loop stops. We call this an indefinite loop because we don't know a definitive time it's going to stop. We don't know how to definitively tell how many times it's going to run. With the for loops we were writing, These were definite loops. It's going to run 8 times. We can tell by this. Here, it's completely, in this case, it's completely random as to how long it's going to take. So we'll have a guest password. Your code goes here. And if the guest password is equal to my password, so if these two things are the same as what this is saying, then we're going to print out a statement to say we found the password and that we're done. We haven't learned if statements yet either. That's okay. But you can kind of get the drift over here. Tell if these two things are the same. If they're the same, we found the password. So how do we go about this? Well, first things first is I'm going to steal this over here so I don't have to rewrite it. Because that would be a real pain. Put it up here. If I put it in the loop, it would basically redeclare the variable each time, which would just be wasteful. Would be wrong, just wasteful. So for blank in range 4, we have to do it's a 4-letter password, as we can see over here. So it's going to go 4 times. And what are we going to do? We are going to say random.choice letters. And we're going to say guest underscore PW. That's what they use for that, plus equals random.choice letters. So it's going to guess those letters. So it's going to do this 4 times, grab a letter 4 times. And let's see if I'll just hit to 30 seconds right now and we'll hit save and run. Found it after 0 tries. Okay, so it found it. 0 tries doesn't seem like it's correct. So what I forgot to do is that I forgot the next part, but I was able to find this, right? I was able to get something after, because if I wasn't able to get these two things to match, it wouldn't have told me that it found it. So now we want to keep track of how many times it took to get there. And we do that by saying guess underscore num plus equals, whoops, not there. That would do it we don't do it there. That would do it every single time every time we added a new letter. We want to create a new guess every time we generate a new word. So plus equals 1 here. So we run it. And it took 38,000, let's call it 39,000 tries to find that password. Run it again. And again, this is random. That took about 3 times as long. And unsurprising, since it took 104,000 tries to guess the password. Everybody following? Right? Again, this part was entitled challenge, and it goes well beyond what you've hit so far. So if you're able to follow along for this part, congrats. You did everything I wanted you to do and everything I wanted you to get out of this lecture. I always like to go a bit beyond, though, and see and kind of stretch ourselves. So here, right, we've got our letters. We're choosing 4 random letters from it and then trying it. And again, it doesn't matter what one we're searching for, so long as they're the same length. Let's see. It's taking a while. Might actually crash out at this time. Right, because it's completely random. And that's why I set it down to 30 seconds. I don't want this to take forever. Yep, exceeded time limit. Okay, let's go ahead and try and change this to 3A's. Sorry, 4A's this time and see how long it takes to generate a password with 4A's randomly. And by the way, that's just as statistically likely as a password as ABCD. And we're here waiting. Now, while we're waiting, we'll do this last part, which is kind of the math here. Oh, found it after 490,000 tries. So let's go ahead and move on to the next part and do the math here. If I wanted, now, Here's the thing. If I made this a 5-character password, this is not almost certainly not going to be able to finish in time. And why is that? Well, there's 4 letters here. Each of those possible letters is a lowercase letter, right? Which is 26 characters, and that's 26 possible characters. So what we're going to do here is calculate the number of combinations there are. If it's a 4-letter password made up of just letters, there are 26 letters in the English alphabet. So there's 26 possible choices. 26 possible choices over here for our first character. One of these letters. 26 possible choices. Then there's 26 possible choices for the second one. So if it was a 2-letter password, there'd be 26 combinations with A starting first, 26 combinations with B starting first, 26 combinations with C starting first, 26 combinations with D starting first, right? AA, AB, AC, AD, then dot dot dot, then BA, BB, BC, BD, and so on and so forth. Okay? Technically, these are permutations, not combinations. So permutations. Okay. So that's why we have a multiply there. A third letter would multiply it like so. Hold on a second. 26 times 26 times 26 times 26. You have. And so what we have here is saying that for a 4-letter password, there are 456,000 possible combinations. 457,000 if we round up. And so adding a 5th letter, the reason it took why it wouldn't complete if we had a 6th letter is because it would take 26 times long. Let's go ahead and shorten this out. 5 letters means that this is 26 to the 5th power, right? So for 8 characters, be 26 to the 8th character, and that's 1, 2, 3. So this is 208 billion. 208 billion different different possible 8-letter passwords. That's a lot. But a computer that's not working in a web browser can probably churn through that a lot faster, right? 1,000 guesses a second is what that was saying. The author said he was going around 16,300 guesses a second. So what we're going to look over here is that, and this is just if it was letters. What if it's capital letters as well? Then each of those have 52 possible combinations. Okay. What if it was numbers as well? What about random symbols? You've got, say, 72 over here, 73, 74, 75, 76, 78, 80, 82. Let's call it 90 possible symbols, although there's probably more. 92. There we go. 92 possible symbols. There's the 8th power. That brings us to a very respectable number, right? For completely random passwords. Millions, billions, trillions, 5 quadrillion. No, this is completely random. This is completely random password guessing. And breaking passwords is typically not done by in this manner. Because if you're using eight characters, it's still within the realm of possibility for multiple computers running in parallel to crack not too much time. On the other hand, let's go back to our using 26 characters, and instead you just compose your character of random words, and let's just assume for the sake of argument that it's not that they don't know you're doing random words. The calculation's still pretty gets still pretty similar results or for random words. But let's say you're doing 4 random words. Assume that password is 16 characters long. You're using four, like we're say we're being really lazy and using four four-letter words. Okay, using four four-letter words. All right. Let's print out our previous result alongside that. Humans have a hard time understanding just how much bigger this is than this. Right? This is going to take a million times, over a million times longer. But this is 10 to the six zeros more than this. And that's not if it's 16 if it's using only 16 characters. If we up it to 5-letter words or 5-letter words, it's not even close. Humans have a really bad time understanding how big numbers work because we're just we're just humans. So, long story short, when you're making your passwords, I do something rather simpler like this, and then add in the random nonsense because that's what the passwords. Because this is what we've done for years upon years upon years. Through 20 years of effort, we've successfully trained everyone to use passwords that are hard for humans to remember, but easy for computers to guess. Why? No grand conspiracy. It's because back in the day that we might have had a limit. I would assume that back in the day there was probably a limit to the length of your password, and so the policies arose from there. And now we don't really care how long your password is. Heck, if we're doing it correctly too, it's not even going to be storing a website isn't going to be storing your password. Nah. Most passwords, by the way, they don't even store your most websites, they don't even store your password. What they do is they do something called they store something called a hash. So um you'll do something where basically it here this is something I did a lot of my research in where basically what happens is that you have a just some kind of phrase you want to identify and be able to say, yes, this is what I used without being able to tell you what I originally used. So let's put in my cool password. This will pump it into an algorithm like this, SHA-256. Not, I think it's not secure anymore, but it doesn't matter. It You pump it into an algorithm like SHA-256. And sorry, you type in your password. What happens is that the computer runs your password through this algorithm and it gets this. This identifier, while not unique, is going to be very close to it. Okay. And so this is what gets stored in your on like in the websites you log into, like Facebook, Amazon, Google. They'll store something like this. Okay. It actually gets more advanced the more, for more companies, but this is the base idea. Don't store this because if a hacker or a infiltrator gains access to your computer systems, you don't want them to read the password file so that they can figure out everybody's passwords, right? They don't want to see it's much if they see, oh, Andrew Rosen's password is my cool password, I'm pwned. That's it. That's it. On the other hand, if they see Andrew Rosen's password is this, that's less useful. And so what happens is when I log in, I'll type in my password. So under normal circumstances, what happens is you log in, type in this password, it generates this and it checks, is this the same as what I've stored? And it goes, yes, these are the same. So he must have typed in the right password. And so that's the idea here. Um, this, of course, is to plug one security hole, which is what if somebody socially engineers their way onto the network, right? We want to make, in this case, now the question is, how can I calculate this? And that becomes its own security problem. All right.